afternoon. I have extremely good news for one of my moderators. I will wait for them to join. Hopefully you're going to be joining Chickpea Break because I have great news for you that I want you to actually guess at. Other than that, I hope that we get this exciting episode, one more exciting episode, live stream episode of this channel going, started, and whatnot. Hello, River, that Essa pointer. Hi. I don't think I've seen that particular username before, so do tell. How are you doing? Who are you? And where are you from? Whatever. Whatever you're comfortable with sharing. Oh my gosh, Chickpea Break. Guess what book? Guess what book I'm about to read from today? Guess what book is about to make a comeback on this channel because the library has permitted me to borrow it again for 14 days. Guess which book? Guess which book we were banished from for a while because I exceeded, gosh, I hope I don't have a booger falling out of my nose right there, but guess which book? Exactly, the correct reaction to this is being given by Chickpea Break. Hello Chickpea Break, hello River, hello everybody. Oh my gosh, 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 oh my gosh. And I did not know that I was indeed gonna be allowed. Today is the day of this millennium that I have been able to re-borrow exactly Mr. Dr. Professor. In fact, it is Professor Dr. Lawrence Krauss's book, The Atom. Oh my goodness gracious, my name is Harper. Hello River. It is you, River slash Harper, that is River tonight. So thank you so much for being here. Thank you, 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 thank you. I am just so excited to be able to bring to you. Today is an auspicious day. Oh my goodness, exactly correct reaction given by Chickpea Break. Exactly correct reaction being given by Chickpea Break. I cannot contain my excitement either. Chickpea, I cannot contain my excitement. I cannot. Please do share the live with everybody you know. Hello MBBS.99M. Hello, how are you doing? It is Machine Gun Heart. Oh my gosh. Well. Hello YTV. Hello Sunflower. Hello Detective Plane. Hello Detective. Hello YT. Hello MBBS. Hello. And please do like the live. Can we get 20 likes? Can we get 40 likes? Can we get 40,000 likes? Hello Ricky or hello Ray. I read that as Ricky, but hello Ray. Thank you so much indeed for liking the live. Ladies and gents, we have an amazing book up for you tonight. Hello Ricky, hello Ray, hello Wraith Nee, hello Hola, says Wraith New York maybe. Hello Chickpea Break, hello Justin, hello. Excuse me? That's weird. Can we get some likes up in here? Can we get 20 likes? Yes. 20 likes, everyone. I'm gonna pin that message. Oh my gosh. Hello, official. Dude, hello. Let's get 1 million likes. Oh my gosh, yes. And there is a kitty cat right there behind me. That is Baji Baba, my youngest child. Oh my gosh, guys. So Chickpea Break, my friend here, my moderator, thank you for timing out an atrocity of nature here. Harper, or whoever it was that timed them out. We need these likes exactly. Hello Lucifer, hello Lucifer, hello everybody. If you want a shout out, just have to type a message, and if it is readable, then I certainly shall give you a shout out in the chat here. So I am just so very excited because my favorite mod here, what you call Chickpea Break, has been requesting this book for forever. He has been requesting this book forever. Hello official, hello Lucifer. And we were not able to cover the book. And of course, we've been talking about string theory. We've been talking about A Brief History of Time by Stephen Hawking. And we've been, showing the kitty cats and myself and my face. And we've been talking also about Brian Greene's The Elegant Universe and what not. Hello, Acacio. Hello, Casey. Hi, Casey Barnes. How are you? I was gone for a while from the net, but I'm back to where I once belonged. Andrew's Physics Channel. Oh my gosh! 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 Let me brush my hair again. I am just so very excited, guys. That book deserves us to wear out the best in you. Oh my gosh! Here, 1 second. I just took a shower, so hello, Casey. What are you saying, honey? What is this UWU, what is that? I don't really know what that means, Casey Barnes, but thank you so much for being here. Chickpea says that book deserves us to wear our best indeed. Oh my god! Oh my god, do you see the gold earrings? It's because we're gonna discuss Ver's book. Hello, Raithney says you're beautiful. Okay, thank you, honey. And thank you, Casey. What do you mean, Casey? I don't know what this UW thing is. Oh my gosh. So by the way, guys, don't mess with my mods over here. Tonight, one of the mods' favorite book is gonna get read today. So if you say obscene things in the comments, he's gonna get too busy with that. And I really want him to contain, or the opposite of contain, his excitement, because he's been requesting this book for forever. Chickpea, are you ready? Say you're ready. Come on. Chickpea, are you ready? Steven says, hi, Steven. I love that book. River, it's Harper. Hello, Casey. Chickpea, are you ready? Chickpea, are you ready? Are you ready, Chickpea? I'm ready for that book. It's been forever. Lucifer. So this book is called Atom. A-T-O-M, like the word atom. This book is also called Atom, and I just cannot contain my excitement, because Ver has been requesting it for forever. The Bahamas, the entire Bahamas, the islands have been requesting this book. This is a wet brush, by the way. I just showered and I still have a bunch of water in my hair, and I just want to take out the water in my hair a little bit. Adam, all right on. Yes. Oh my god. Do you have ferrets? I don't know what that means. Hello, Culum. That book is why I'm the best mod right now. You are. Oh my god. So Ver didn't used to be a mod. At some point, he became a mod. Before that, he used to kind of like want to see food channels only and whatnot. And I think he even got on this live because he thought that there would be food somewhere. Exactamente. Oh my gosh, Acacio, are you ready? What do you think of my book so far? Oh my gosh, Steven, thank you so much for sending the book preview. I'm going to do a reading from that probably on Sunday or Monday. And if you want me to read a full chapter, I can even do that as a members only video as well. There's food here. There's chickpeas. There is chickpeas here. Chickpeas, what fuels me and my excitement. Oh my gosh, Acacio. Oh my gosh, Ver. I took a shower and I have too much water in my hair still, so I'm just getting it out. And I'm waiting for everyone to say how ready they are to hear the book Atom by Dr. Professor Mr. Lawrence Krauss in the house. This made my entire day for real. Oh my gosh. Me too. So because I was thinking I'll continue the state of string theory today. Like we were going to talk a little bit about Edward Witten and his work on string theory from the Elegant Universe, the book called The Elegant Universe by Brian Greene that we have been covering recently. But today, on my phone, I get a notification from Libby, the library app, of course, that they will allow me to borrow this book again. Adam, they let me borrow the book, but then they took it back too quickly. Like I only had a week or two with it the first time, and now they're gonna give me another 14 days with the book. And it's not a book that they had as a hard copy, so I had to get it on the app because I'm not one of those people who really reads from their tablets or anything like that, or like their phones too much. I'd rather have the physical copy of the book. And we were even thinking like we should just ask Lawrence Krauss to send a copy, and I was about to. We were gonna cover the other things, and you know, but I do like to mix it up. Like we have been talking about string theory for a few lives, and so Conan Gray. Who's Conan Gray? Who is this? What are we talking about? Hi Casey, hi River, hi Acacio. Sounds as good as Indeed. I'm crying. Who is Conan Gray? I don't understand, but okay. So I am not one of those people who will read from like their tablet or their phone and that's it, right? I'm more of a physical copy reader, but this book, they didn't have this. I couldn't find it physical copy. So I'm tapping on my iPad here. Look at this. I've got the book up and ready for you guys on my iPad. So by the way, I'm late to the live, but I was working on getting this book up and ready on my iPad because the Libby app was only on one of my other, like on my phone that was the broken phone. Then I got it downloaded on my iPad, and I'm gonna be reading to you from this iPad subsection or sections out of the book, okay? So this is the book, Adam. Dr. Professor Lawrence Krauss is the author. This is a guy that I've actually met in real life, and I've even taken him to McDonald's. So Dr. Krauss, if you ever see this video, you should know I was that girl around, I don't know, 15, 16 years ago when you came to NC State University, North Carolina State University, where I went to do undergrad in physics. And you came, Dr. Krauss came to do a talk and a debate. I think it was actually about like God and whatnot. Like it was like, does God exist? Is there evidence for that or not? And he was debating some other guy, some religious, spiritual type of guy. And it was a very fun debate. And of course, Dr. Lawrence Krauss is a physicist himself. And that's why we all physics majors and all physics undergrads and grads went to the talk. And we, of course, looked up to him as a role model in physics. And all of us were asking, we were more interested in the physics work that he had to share and all his research and everything he had to say about like cosmology and oh my gosh, oh shut up, of course McDonald's is better than Five Guys. Are you saying that Five Guys is better than actually never been to Five Guys. You know, I'm not from this nation originally, and I haven't tried all my fast food options. You know, fast food is not really something that we aspire to constantly, but McDonald's is my favorite fast food. Am I wrong or am I right? Wait, I should have said, am I right or am I right? Am I right or am I right? So anyway, we were interested in his physics work, and I suggested, me, myself, yours truly here, I was just a little undergrad at that time, but I was like, Dr. Krauss, do you want to go to McDonald's with us and we can all sit and eat and talk about physics? And he said yes. He said yes. And then we also talked about my hometown, where I'm from in Kolkata, and he said that he had visited there for work. He had been to IIT Kharagpur, which is close to where I'm from. It's an IIT, Indian Institute of Technology. It's one of the IITs, you know, Indian Institute of Technology. And he said that he had visited there for a lecture or like a talk. And he said, oh my gosh, the traffic where you're from is really crazy. I hope you don't move back to India. Well, Dr. Krauss, here I am, still in North America. So here we are. And we're going to be reading his book, at least one of his books. I believe that he has probably more books than this one. And he has especially contributed to cosmology, as far as I know, to work about the universe and things like that, you know, Big Bang, all that stuff. So those are really topics that interest me a lot, that I'm very curious about myself. My PhD is, of course, in particle astrophysics, so kind of related, but not exactly the same as whatever Dr. Krauss has worked on. And this is actually why I like to read books by authors and on topics that are not exactly my exact subfield that I might have expertise in, or do have expertise in, or did study a lot, because then I can also broaden my horizons and I can also learn more, and especially kind of learn more about related topics and related things that interest me, that are very that pique my curiosity, and that I'm interested in. Okay, so we will definitely go back to more of the string theory stuff that we've been talking about. Hi MBBS, hello, and whatnot. We've finished up pretty much everything that we were covering from A Brief History of Time by Stephen Hawking, of course. But that book too, some of the things that we learned from that book, we will kind of rehash and review as we keep going, because Stephen Hawking gave us some nice insights, and of course his work with black hole, Hawking radiation, how black holes do this, quantum dance sometimes, and the quantum fluctuations can explain how black holes can have a temperature, etc., etc. will also kind of keep on coming back up. Okay, so those types of things we will take with us going forward. And by the way, if you're new to this channel, you should definitely like, share, subscribe, tell everybody about this, about this live stream episode and the channel in general. This is a Cats and Physics channel. Like, all of the wonderful things of this universe come together on this channel, hosted by me, yours truly. So I'm the host of this channel, and we cover kitty cats and physics, quite literally. My children are kitty cats. See, one of them is right there. And physics is one of my favorite topics. It might be the favorite topic intellectually. And you should also become a member. Yes, Stephen is correct. See, Stephen here is a member. So please do like, share, subscribe. And please do know what that this channel is about cats and physics. So if you enjoy those, you might just learn something new. And there is a lot of cuteness overloaded type of videos that come out regularly on cats, as well as on physics lectures, physics lessons, and we cover astronomy, astrophysics, and cosmology. Okay, those are my favorite things. And so I'm going to be talking, I'm so excited today. I'm going to be talking about this book, Atom Now, going forward, and I'll give my own insights as well, and my own explanations and little tidbits here and there. I wanted to share the story of Lawrence Krauss, just because I didn't meet him, personally as well. And some of the authors, by the way, some of the other authors on this channel that we've covered are also people I know personally, that used to be my professors or my bosses in the past. So it's always good to sort of have a feeling for like the person that write these books and share their insights and whatnot. I have to go. I'll see you soon. Bye. Bye, Harper. Thank you so much for being here. Welcome to everybody else. And can we get 20 likes? Can we get a super chat? Can we get your subscription? Can you please like, share, subscribe, become a member, or do a super chat, please? Thank you, Elon. You are from? I'm in North America. I'm in Boston, but I'm originally from India, from the city of millions called Kolkata, in the eastern part of India, on the delta of the river Ganges, holy river of India. So, oh, are you ready? Say it once again. Are you ready? I'm going to take a sip of my water. And are you ready? Are you ready for Atom? Are you ready for this book? So by the way, we have already covered a little bit. That's from the beginning of the book. So we're going to get started at this exact sentence that I'm about to start saying right now. But are you ready? Chickpea, are you ready? Are you ready? And soon we will be, exactly. So we're also launching some people's books on this channel who are members of this channel. And gosh, your present address. Do you want my address? Oh gosh, well, I am in the USA, yes. I probably shouldn't be any more specific than that, given the situation here. Eversource says, I'm so ready. Okay, we're gonna get started. Okay. So we're also launching some people's books here on this channel. Steven is one of them. Steven is a member. So if you become a member of this channel, or if you come to the live streams a lot and you contribute positively, then chances are if you wrote a book or if you have a science fiction novel or a science novel or a science paper that you want to share with us on the channel, we are happy to launch it here, okay? So Stephen actually sent me a part of his book, which I'll be reading soon. I'll do a reading of that probably Sunday or Monday, okay? So with that, I'll get started with tonight's author. Oh my gosh. This is Professor Dr. Mr. Lawrence Krauss's Atom, okay? We begin when what is now the entire visible universe of over 400 billion galaxies, each containing over 400 billion stars, each 1 million times more massive than the Earth, encompassed a volume about the size of a baseball. Gosh, the simplicity of this statement belies its outrageousness. It is impossible to intuitively appreciate this era by making the leap from here to there in one giant step. But it is possible to imagine a series of smaller steps, each of which itself pushes the limits of visualization, but each of which gets us closer to fathoming the truly extreme environments we're about to enter. So he's going to talk about some very extreme things now going forwards, okay? So hopefully you're ready for that. Our first step begins with our own sun. So by the way, I should mention that our own sun is quite young, quite far from dying, and it is constantly burning for us and turning hydrogen into helium, and that's how we get light, energy, heat, and all that good stuff from the sun, okay? Let's see what he has to say. But sometimes when stars are much, much more massive than our sun and closer to their death, they can die and turn into these more compact objects, namely white dwarf, neutron star, or black hole. So those are the three options when you die and you're a star, okay? Let's see now what Dr. Krauss has to say. Our sun is far from its death at the current moment. It's actually gone around the galactic center of our own galaxy, of course, the Milky Way galaxy. It has gone around our galactic center only about I believe it was like 21 times only. So in that sense, it is barely more than a teenager in the sense of this galaxy, okay? So our first step begins with our own sun, almost 1 million times as massive as the Earth. So indeed, the sun is much, much bigger than our Earth. Now, I don't know if we should even really compare our Earth with the sun. The sun is a star. By the by, hello Jeep, hello Stephen. By the by, we all come from a gigantic gas nebula, quite metal rich, which condensated to make the sun and its planets, in other words, this solar system of which we're a part. And a little bit above 99% of the mass of this gigantic gas nebula actually went to our sun. So of course we are much, much smaller than the sun, the Earth, the planets are much smaller. And guess what? Most of the mass went to the sun, but most of the angular momentum went to the planet. So that's why we all rotate on our axes. Well, some of us don't rotate very much or rotate very slowly, but we also, the Earth is spinning on its axis, it's going around the sun, blah, blah, blah. That's because we carry a lot of this angular momentum from the gas nebula, but we don't carry most of the mass from the gas nebula. That is the sun that carries that. And of course, the sun is a star. We cannot really compare a planet to its star, right? The sun is its own thing. The sun has a nuclear power plant in its belly, and it's constantly doing nuclear power, turning hydrogen into helium. So it's doing nuclear reactions. That's how it stays burning. That's how it stays alive. That's how it gives us everything we know and love, light, heat, energy, right? So the sun is a star. We are a planet. There's no nuclear power plant in our belly. We have a core. It has some iron. We have other layers on top. Blah blah blah. We have rock. We have lava. All that. But we're not burning any element to make another heavier element like what stars do. So we're definitely not. We're not the same, right? Now Jupiter is a much bigger planet that has interesting things, but even Jupiter is a planet. It doesn't have a nuclear power plant in its belly, okay? So anyways, but I wanted to give you a little tidbit of our own solar system so you have some idea. what is what. So almost 1,000,000 times as massive as the Earth. At its center, the temperature is almost 15 million degrees. 15 million degrees, right? So compare that. If you look at the star Betelgeuse, it's going to supernova. I meant in our galaxy. Oh yeah. So Betelgeuse. So by the way, Betelgeuse is spelled as Betelgeuse. I do believe. Please do check my spelling, but it's not beetle juice like the fruit juice type of spelling, right? Betelgeuse. So Betelgeuse is a red giant. So we do expect it to supernova. Correct. It may have already supernovaed and we just don't see the light yet from it. I forget actually the distance that it is at from us, but indeed when something is as so when the star has different stages of its life cycle. If it's closer to sort of a red giant or more in the life cycle, then we expect it to die and supernova, especially the more massive stars. Remember, why do the more massive stars die quicker? Because it needs to burn more power to stay alive, because of course the star is doing all this nuclear power against its own gravity. If the star ran out of nuclear power, then it would collapse under its own gravitation, because stars are massive objects with a lot of mass that are of course going to try to collapse, pull down and basically collapse on itself. So there's two main things going on in a star. It's gravitation, which will try to make it collapse, and nuclear power, which it does to convert some element into heavier elements, and that's what keeps it alive. Now, the bigger the star, the more power it's going to go through, the more it needs to keep burning in order to keep burning, and so it runs out of its fuel faster. So if something is already a red giant, it's gonna be dying faster, for example, than our own sun, which is still on the main sequence. I wanted to say main sequence. So it's still definitely kind of going through its different stages, which is far from becoming a giant. Okay, so once a star kind of becomes a red giant, you expect it to kind of die at some point soon. But if it's on the main sequence, sort of what our sun is doing right now, it's just converting hydrogen to helium, and its mass is not that much. Okay, so let's keep going with the book. A little bit of tidbits about stars and whatnot for you. Our first step begins with our own sun. Hello, Jeep. I'm not sure what you're saying with that 75 thing. Oh, I see. I believe it's like 75 light years from us. So it's going to take 75 years for light to travel from it to us. So if it is 75 light years from us, so light year is a distance, it's going to take... So 75 times the speed of light is the distance it's away from us. And so it's going to take light 75 years. Okay, got it. I actually don't know, but please do double check exactly how far Betelgeuse is from us if you're interested in its supernova timing, okay? But also, at the same time, astronomy doesn't have to happen with regard to our own timelines and our human timelines. Astronomy, cosmology is more at the timeline of like giga years. So a giga is a billion, right? So billion year type of things, like the sun is around 3-4 billion years old, 4 billion years old. So that's sort of the more timeline of things. Betelgeuse, I mean, it could be a million, couple million, a few 100 million years away or something, so even the millions of years is considered short in astronomy. So just be careful when you don't hold your breath when you are expecting something to supernova, okay? But Betelgeuse, I mean, even when I was in undergrad, we were thinking that Betelgeuse will go off anytime now. So you have a point. So, but again, that's a human timeline. So, so our first step begins with our own sun, almost 1 million times as massive as the Earth. At its center, the temperature is almost 15 million degrees, cooling by more than a factor of 1,000 at the surface to a mere 6,000 degrees. So 6,000 degrees Kelvin is so much cooler than the middle of the sun. Middle of the sun, of course, has this nuclear power plant in its belly. So 15 million degrees at the center, 6,000 degrees on the surface. Quite a difference in terms of temperature within the sun. So about twice the temperature of boiling iron. So 6,000 degrees is not that bad. Like if we wanted to do something quite extreme here on Earth, we might reach hundreds or thousands of Kelvin temperature, right? So nevertheless, the sun's average density is only marginally greater than that of water. Not much different than the average density of the Earth. If we squeeze the sun in radius, so the sun's average density, Betelgeuse is 650 light years away. Thank you. That makes more sense, but I would keep checking. Just don't take my word for it or anybody's word for it. Betelgeuse, B-E-T-E-L, yes, B-E-T-E-L-G-E-U-S-E. So just look it up exactly how far Betelgeuse is, and it is for sure, I believe, a red giant close to its death, okay? So isn't it so interesting, even though the sun is so much bigger, it has 15 million degrees temperature at its core, 6,000 degrees on the surface. It's a nuclear power plant turning hydrogen to helium, but if you think about it, the average density of the sun is not so different from the Earth. It's almost like we all came from the same thing, the same gas nebula, like I was mentioning. Some gas nebula, some enriched, metal-rich gas nebula condensated to make the sun and its planets. So ultimately, we are kind of like little children of the same thing, and we're not that different, but we're kind of different, right? So, of course, Earth is much smaller, and it's a planet. It has cooled down. It's small enough to have cooled down, and it's not big enough or hot enough to be doing any nuclear power stuff. So here we are, you know, and we have made oceans which have cleaned up the atmosphere of the Earth, and that's how we can breathe, and that's why we're here, you and I. So that's really what's going on. You know, if the sun were to be smaller, maybe it would have been a planet, but it's not. It's the sun. So sun's average density is only marginally greater than that of water, not much different than the average density of the Earth, because of course Earth mainly has water on its surface anyways. If we squeeze the sun in radius by a factor of 10, so that it is now 10 times the radius, of the Earth, it is now much denser than any planet in the solar system. A teaspoon of its material would, on average now, weigh several pounds. So if you squeeze anything a lot, it becomes more dense, because density is basically just mass divided by volume, right? So if the same mass now exists in a smaller volume, it's going to be more dense. And a teaspoon, meaning a very small volume, a teaspoon, meaning a very small volume of material, will now weigh a lot more, okay? So a teaspoon of its material would, on average, now weigh several pounds. Compress the sun by an additional factor of 10. Now the size of the Earth. So the sun becomes the size of the Earth by volume. With a mass 1 million times as great, each teaspoon of its material weighs several tons. So this is to give you an idea of what happens when you compress something like a star. The average density of the star at its current volume, at the bigger volume, might be kind of similar to the one on Earth, the density on Earth, but once you compress it a lot, which is, by the way, what I was talking about a minute ago, stars, when they die and they collapse under their own weight or their own gravitation, will then become very compressed, very compact objects, and these have few different options of compact objects that you can be when you are a dying star, and these are namely white dwarf, neutron star, or black hole, depending on how massive the star is in that order. And so I think he's kind of going towards that, basically. So now the size of the Earth, with a mass 1 million times as great, each teaspoon of its material weighs several tons. Compress the sun now by another factor of 1,000. It is now about 6 kilometers in radius, the size of a small city. So by the way, neutron stars, we know, are basically the size of a small city. right? Size of Manhattan, around 10 kilometers or so. So that's kind of where he's going with this, I believe. A single teaspoon of its material weighs 1 billion tons. That's billion with a B, B for boy. The amount of work required to perform this feat of compression, by the way, is equivalent to the total radiant energy released by the sun over the course of 3 billion years. So the sun is releasing energy. That's how we can survive. But if you wanted to compress the sun a lot, by the way, that's actually work like gravitational potential energy that would be changing, or, you know, that's the energy of it. And the energy to compress it is not for free. It's not like you go to the shop and you ask for a sun compression for free. It takes work, and this work, which is equal to energy, would be equivalent to the total radiant energy from the sun over the course of it could have kept us warm for 3 billion more years if it didn't get compressed. Now let's see what this compression story is about, as told by Lawrence Krauss. But as I was mentioning earlier about the fate of stars, really the fate of stars is compressed objects, because once the star stops starring, once the star stops doing nuclear power, there is just nothing that can fight against its own gravitation, and it generally will fall and compress. Some of the mass will go everywhere else, like will just go out into outer space, into the interstellar medium. That's how, by the way, we have gas clouds just floating around sometimes, is because it comes off of stars. Like in the course of the star's explosion, in the course of its supernova, sometimes a star will do a big shedding of its outer masses into the outer space, just into the interstellar medium. That's actually how we have a bunch of gas in interstellar medium. Even we come from such a gas cloud or a nebula, okay? So when a metal-rich star dies and ejects its outer volumes into the interstellar medium, if the star was very metal-rich, then the gas going out will be metal-rich. We are pretty metal-rich. We even have gold on Earth, right? Gold is a very heavy element, aurum, on the periodic table. You can somebody look up what is the atomic number of gold. So that means we come from a pretty metal-rich gas nebula that condensated to make the sun and the planets. And so we didn't just come from any old nebula that didn't do much, or came from a star that didn't do much. We came from some star that died that did a lot, and the stars before then, that star did a lot. And then they died, and then they shed their outer layers into the interstellar medium. And then years passed, and then that gas cloud coming from such a star's death condensated, cooled down enough to make the sun and the planets, and that's how we're here. So we come from such stars dying for us, okay, if you will. So 79, okay, very good. So I guess that means that gold has 79 protons in its nucleus. So gold has, wow. So imagine the universe got started with just hydrogen and helium. This has 1 proton and 2 protons in the nucleus. So from 1 or 2 protons, making gold, which has 79 protons, you're telling me, is a lot of work, right? Taking all those lighter elements like hydrogen, 1 proton, helium, 2 protons, lithium, 3 protons, beryllium, 4 protons, boron, 5 protons, right? Going from that to 79 protons in the, am I saying this word right? Protons, right? Sometimes I get the particles mixed up in my brain, especially when I'm speaking. Protons, neutrons, yes, that's in the nucleus. So going from something like lighter elements like hydrogen, helium to something like gold is a lot of nuclear power that happened. It's a lot of nuclear fusion that happens over and over and over in the course of stars' life cycles to then give us something like gold. And then that star died, and then it ejected its material into space, and then that material went and formed a gas cloud, and then that became a nebula, and then that cooled down to making something like our sun and us. And that's how we have gold. See gold right here. I mean, this is probably just gold plated, but that's how we have gold in our jewelry and everything. Don't take it for granted. Do not take it for granted. Gold and silver and uranium. I mean, they make, they made atomic bombs out of that, right? So uranium is what, 92, even heavier element. So don't take these elements for granted. Stars have lived and died for them. Lived and died. Heavier elements come from stars, period. Stars have lived and died for these elements. That's how we have these elements now, okay? So anyways, at this density, the atoms in the sun lose their individual identity. So, what the person is saying, Muscovium 115. No, it's an Arabic word. Oh, I don't know. Betelgeuse? It could be. So, Dr. Krauss is saying that when you compress the sun a lot, so we know that the sun right now at its current average density, which is not so different than Earth's density, has hydrogen and helium in it, so it's going to be hydrogen going to helium. So the sun is a baby star. Where as far as stars go, the sun is a baby star. It's just making helium from hydrogen. That's a pretty early on kind of nuclear reaction, as you can tell. I mean, there are stars and there are environments in which heavier and heavier elements have been made all the way up to iron and more. As in iron is only 26. Somebody correct me if I'm wrong. Atomic number of iron, what is it? Is it 26? Somebody check that. And then barium is something like 56, right? And then aurum, gold, argentinum, silver, uranium, these are all heavier, right? So if a baby star is making from hydrogen to helium, hydrogen is atomic number 1, helium is atomic number 2. So it's still doing a baby nuclear step. Good. That's why we're here, and that's why, the sun will be around for a while, because if the sun were making something too heavy and it kind of runs out of its power because it's nearing the end of what's possible easily as far as the nuclear reactions go, then it'll actually run out of fuel, right? And it'll stop burning and it will collapse under its weight, and that's actually how stars die. So it's a good thing for us that the sun is only making helium out of hydrogen. It's still doing that early stuff, right? That's a good thing. Because another thing to note also is that if you make elements, this is a little bit of nuclear physics talk that we're injecting with this discussion, okay? If you make, in nuclear physics, if you make nuclei that are very stable, actually helium is quite stable, or if you make the most stable nucleus is iron, okay? The iron nucleus is very, 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 very stable. This is this thing called nuclear binding energy. Higher that energy is, the more stable that nucleus is, right? So if you make very stable nuclei, then basically the nuclear reaction to make even heavier nuclei is going to be needing more power, and it's going to be more difficult. It's almost like those particles want to be in that stable state. They just want to be happy as iron nuclei, right? They don't want to be disturbed anymore. Like they're like, we're done, right? So there's more details as to why, but the nuclear physics is that if you make very stable nuclei, then then it won't want to do heavier. So another way in which stars die is they actually start to have an iron core at its in the belly, right? So when pretty much everything in its core has been converted to iron, like because it goes from the hydrogen to the helium to the higher to the higher to the higher to the higher, pretty much to atomic number 26 that somebody said is iron, right? Once you've made iron and you have an iron core, it's going to take more energy to make the heavier nuclei. And people as in the elements in that star are not going to be happy to go to the heavier nuclei. It can be done with more energy, but it's just harder. So then a lot of times actually the star will supernova, and it's called a core collapse supernova, when a big telltale sign is when the belly of that star is made of iron. Once the core is made of iron, it has a big gigantic iron core. If you really think about it. What are the chances of trees evolving? Well, trees are mainly just carbon, hydrogen. I'll come to your question in just a second. That's a great point. But if it has an iron core, then that actually means that it's kind of it's in danger of doing a core collapse supernova, because it's gonna take more energy to keep on making the heavier and heavier elements from there. Okay, so keep that in mind. And we have actually talked about core collapse supernova as one of the ways in which, because there are a few different types of supernovae as well. There's like 3 types of supernovae that we have talked about, and core collapse supernova is one of them. It's the very massive stars doing a supernova, and it's called core collapse supernova. And in that case, usually there's always a core of iron in the belly of that star, meaning that all of the elements, they have all built up to iron, and now to make the even heavier elements needs an even more extreme environment, and instead it might just core collapse. Okay, as in the gravitation is winning. As soon as gravitation wins, a star is going to die. Okay, so if you really think about it, tree wood is the rarest natural resource in the universe. What are the chances of trees evolving? I mean, the chances of trees evolving is not, I mean, it could evolve. Trees are just mainly carbon, hydrogen, nitrogen. They're not made of like gold. Gold is really rare. It's hard to make gold. I would say the reasons for our Earth being so special is its distance from the sun. It allows us to have oceans is like the reason. Having liquid water is like the reason for us being so special. We have a lot of liquid water which actually help to clean up our atmosphere, because our atmosphere used to be poisonous like the Venusian atmosphere, and when that is the case, it can be very difficult for life to thrive on the planet. Okay, so, and also actually plants helped to clean up the atmosphere as well, because plants were some of the first types of life on the Earth, and they also take in carbon dioxide and release oxygen. So actually oceans and plants are both important for cleaning up our atmosphere and making it less rich in carbon dioxide, which would have been very hard for us to live with, so, or to evolve. Lighter elements are more, yes, the most abundant. So Acacio asked, lighter elements are more abundant than heavier elements in our young solar system. Acacio is asking if lighter elements are more abundant. Lighter elements are just more abundant in the universe, period. The most class, what is the most abundant element in this universe? You have to know this by now. Come on. Not just our solar system. What is the most abundant element in this universe, class? You have to know this by now. Stephen? You're close. Yes, hydrogen. Yes, good job, class. Don't you get this wrong. Don't you, good job, everybody. Don't you get this wrong. The most abundant element in the universe is still hydrogen. Even though the stars are doing a lot of work to convert hydrogen to helium and above, but the most abundant element in the universe is still hydrogen. It's still hydrogen, because, the universe is still young, I guess. You're not going to beat hydrogen. Hydrogen is what we got when we were born. When the universe was born from the Big Bang, it got hydrogen. So hydrogen is still the most abundant element in the universe. It's not the most abundant here on Earth. Earth is special. Guys, Earth is special. Earth is not a reflection of the rest of the universe, okay? As far as I understand, and as far as we know observationally, Earth is extremely special. So don't confuse what is the most abundant here on Earth and what is the most abundant here on the Earth's atmosphere versus the rest of the universe. Overall in the universe, the most abundant element is hydrogen. The next most abundant element is helium. So Stephen, you get second prize. Helium is the next most abundant, because that's what the universe does. The universe does not deal in gold and silver and uranium and iron. I mean, sure, iron is getting made in the bellies of lots of stars, but stars are still a small part of the universe, right? So stars are, there's a lot of gas in the universe. There's much more gas actually in the interstellar medium. Basically what we call interstellar medium has gas, right? Gaseous substance. That stuff is mostly hydrogen, okay? It's not that complicated. It's not that rich in it's not like gold and silver is floating around in space, okay? It's hydrogen. The stuff that's in the interstellar medium You said not to take those heavy elements, but yeah, yes, and you should not take the Earth for granted either. So the the interstellar medium is rich in gaseous substances, and that gas has a lot of, it's mostly hydrogen. So once again, in the universe, the most abundant element in the universe is hydrogen. As we read this book called Atom, you should probably keep in mind the most abundant element in the universe is hydrogen, okay, followed by helium. It's true that stars make elements, heavier elements than hydrogen and helium. Even iron comes from stars living and dying. Gold comes from stars living and dying. And yes, don't take any heavy elements for granted. I mean, even iron is made in the stars. How do you think we got iron in our belly? We didn't make that iron. The iron is more dense, so because of chemical, what's the word again? Chemical differentiation. So this is a geology take now, or not a take. It's just now we're speaking geology, because the Earth doesn't do. It's not like there's astronomy reasons for why we have an iron core. We have an iron core because stars have lived and died and given us iron. And we come from a gas cloud from the death of stars that used to be metal rich, etc., made metals. Now we are here. We have made Earth and the other planets in our solar system. But as far as geology goes, iron is very heavy. So in the Earth, iron has sunk to the bottom, and so we have an iron core. It's not like we made that iron, right? So do not take the Earth for granted. Do not take iron for granted. That still holds true for us, okay? Yo, it's me, Ian, your old friend. Hi, Ian. How are you? Hi, Stephen. Hi, everybody. So do not take iron for granted either. No, we did not make that iron. It's not like we made the nuclear reactions that gave us iron. We were gifted iron from nature, and that iron simply sank to the bottom, which happens to be the middle of this mostly spherical Earth, because it's more heavy, okay? At this density, the atoms in the sun lose their individual identities. So if you squeeze the sun a lot and make it more dense, then the atoms in the sun would lose their individual identity. They would do other phenomena than the normal stuff, okay? Like than normal nuclear physics. Under normal conditions, a single atom is composed of a dense nucleus made up of the elementary particles called protons and neutrons, which are themselves made up of smaller fundamental particles called quarks. Yay! I saw a documentary on mining. They found a mountain of copper in Southeast Asia. Well, don't take that copper for granted either. Copper is which atomic number? Copper is zinc. I think it's 29. So do not take copper for granted either. We did not make it, I assure you. What we made is actually oceans. We did make oceans, so maybe we can take the oceans for granted. But even then, I wouldn't, because what's in the ocean we did not make. I'm going to Kansas. Very nice. So, good thing that Dr. Krauss is giving us a reminder on the atom and its, individual elements and things like that, individual parts. So there's the nucleus, it's got the protons and neutrons inside a nucleus, and as you know, because we've discussed it earlier in particle physics, neutrons and protons, again, are made up of quarks. Okay, so quarks are a fundamental particle that make up the subatomic particles called protons and neutrons. We used to think that the proton might be it, as in it's a fundamental particle, that's it. Later on, the neutron was actually discovered, and then later on, as particle physics made more progress, we actually saw that quarks, these more fundamental particles, make up the protons and the neutrons. Okay, so all of that is to say that, by the way, let me give you a little reminder. There are 3 fundamental particles. These are leptons, quarks, and bosons. We have talked about examples of these things. Leptons are, for example, something like an electron is an example of a lepton, and quarks is another fundamental type of particle which we're mentioning here, and bosons are something like light, photons. Light is made up of bosons known as photons. So that sort of stuff. So Quarks are fundamental particles that can make up something like that, do make up the protons and neutrons that are in our regular atoms. The nucleus contains more than 99.9% of the total mass of the atom. Oh wow, abandoned gold mine. Goodness. There's an abandoned gold mine about an hour from where I live, but it's here in Virginia, not California. Consciousness is fundamental. So typically the nucleus contains more than 99.9% of the total mass of the atom. It is surrounded by a cloud of electrons that occupy a space more than 10,000 times larger in radius than the nucleus, but carrying almost none of the mass of the atom. So you might know that atoms, by the way, the name of this book is also called Atom. Atoms are kind of empty, as in the nucleus is very dense and the sort of volume occupied by the nucleus is much smaller than sort of the cloud of electrons that surround the nucleus. And it's only one electron in the case of the hydrogen atom and only two electrons in the case of the helium atom. But consider if you had a bigger atom than that of one of these heavier nuclei that we're mentioning, then of course there would be more electrons in more such clouds that surround the nucleus. But actually it's kind of empty because the nucleus is not occupying that much space in an atom. By cloud, I actually mean nothing of the sort, says Dr. Lawrence Krauss. Cloud is simply a name we give to the electron distribution because we have no real appropriate label. It is impossible to describe in words what the electrons do as they surround the nucleus. At this scale, they are described by the laws of quantum mechanics. Remember our favorite topic, quantum mechanics, how people were very upset indeed that quantum mechanics has an uncertain and probabilistic nature, and we can't always say where a particle really is. We would only know its probabilistic distribution. So that's what's going on here. So something like electron, it's so small, it does not follow classical physics. It follows quantum mechanics or quantum physics. And in quantum physics, answers are given as probabilities, not as certainties, okay? So it's impossible to describe in words what the electrons do as they surround the nucleus. At this scale, they're described by the laws of quantum mechanics, my favorite, under which material objects behave completely unlike they do on human scale, so that our normal experience is no guide whatsoever. Individual elementary particles such as electrons do not behave like particles. They are not localized in space when they're orbiting the nucleus as planets are when they orbit the sun. Rather, they're spread out. I see this even though we know that electrons can, under certain carefully controlled conditions, be localized on scales so small that we have not yet been able to put a lower limit on their intrinsic size, with no evidence whatsoever of any internal structure. Our language, derived from our intuitive experience of the world, has no place for such behavior. So even our language is limited in terms of what we can say about quantum mechanics, because quantum mechanics is not very intuitive always. It developed in the 20th century largely, and it was considered to be very bizarre and very different than classical physics, and our language is more the language of classical physics, which we've known for centuries, versus quantum mechanics is more recent if you think about it. So even our language, we can't quite fully point out or say in these words what we mean really about these electrons' positions and probabilistic distributions, blah blah blah, of particles and things that happen in such small scales, okay? That's a great point. But the electrons in an atom are not spread out over all space, merely in a volume approximately 1,000 billion times larger than the volume of the nucleus. When we compress the sun to the size of downtown Washington, D.C., we squish the atoms to the point where their electron clouds are essentially pushed inside the nuclei, which in turn are touching each other. So once again, when we compress the sun to the size of downtown Washington, D.C., like 7 kilometers, 8 kilometers, whatever the downtown Washington DC size is, we squish the atoms to the point where their electron clouds are essentially pushed inside the nuclei, which in turn are touching each other. So everything has a lot less space now, very crowded indeed. When you really compress something like our sun to such a small radius, the atoms, same as the title of this book, atom, they're not as comfy. They don't have as much space. They don't have as much space, okay? They really don't. They really don't. Wow. So everything's touching everything. It's like, oh my gosh. It's a little bit like where I'm from, Kolkata. Very populated indeed. And you don't have a lot of personal space there. So the entire mass of the sun is then essentially like one huge atomic nucleus. Goodness. It's almost like everything is touching everything. Which one is which nucleus? Which one is which electron? We don't know. All the atoms are like uncomfy. Nuclei are touching each other. Electrons are touching each other. Everything is like, you know. So it's almost like it's one huge atomic nucleus. One huge. Almost like same everywhere, right? As bizarrely unrealistic as such a scenario for an object like the sun may seem, it actually happens about 100 times every second in the visible universe. Oh my gosh, oh, I love that. Hello, nerd. In our own galaxy, about once every 30 years, the inner core of a star ends its life. See, he's talking about supernovae. He's talking about supernovae now. Oh my gosh, oh, I love it. And did you know, in our own galaxy, about once every 30 years, the inner core of a star ends its life in such a state after a massive stellar explosion, a supernova of the type that created us. See? I told you about gas nebula and about gas clouds condensating and cooling to make us. See, now he's talking about it too. If I had a professor like her, I would have a PhD. Aww. Well, you should definitely go get your PhD. Many people do. If I had a professor, can you believe it though? Can you believe it? As bizarrely unrealistic as such a scenario seems, where the sun's things are all close together, same everywhere, it actually happens about 100 times every second. That's how common it is, and that's how much stars die to make people like us. Oh, isn't that romantic? Let us keep on compressing. PhD takes like 10 years to earn. So, are you calling me old? I did go to school for 10 years, it's true. It's more like 9. I did 4 years undergrad, 5 years PhD, so 9 years in school. Not that bad. So, let us keep on compressing. Take this gigantic solar atomic nucleus of mass, 10 to the 56 times the mass of a hydrogen nucleus. So because you've compressed it a lot, it's kind of like one giant nucleus, right? So it's a 10 to the 56 times the mass of a hydrogen nucleus because of all the different nuclei that's in there. And compress it further by another factor of 100,000. So that a single teaspoonful of material now weighs 1 million billion tons, the mass of 1,000 Earths. A teaspoon of material of this more compressed sun, in imagination, would weigh 1 million billion tons. The sun is now the size of a basketball. So, if you compress the sun somehow to the size of a basketball, no worries, you would just make a teaspoon of it weigh 1 million billion tons only. So then what happens? We'll see. I'll be out in my 50s. And you'll be 50 even if you don't get a PhD. So just get a PhD. I think we will all turn something at some point, and that's no excuse to not get a PhD. If you want a PhD, go get it. You'll be 15 regardless. However, there are about 400 billion suns in our galaxy. And actually my office mate in grad school was in his 50s. One of the office mates. I had a very large office in grad school with the blessing of the universe, and I had 2 office mates, And actually I switched groups a number of times, and then I was finally in this much better opportunity where I got my PhD and it worked out. But I don't regret anything, because of all my rotations in grad school, I actually learned more physics, not less physics, right? So it's all good. But there were a lot of uncertainties related to where the heck I would end up and whether I would even have a PhD or not. So I guess I'm okay with uncertainty in that sense, and how quantum mechanics, you know, requires uncertainties, deals in uncertainties. Anyway, so finally the group in which I got my PhD, that office, the office I was sitting in as an RA, research assistant, had two other office mates. One of them was like my age, and the other one was well above his 50s. He had a whole career. He did his whole, like, he was a software engineer in IT, etc. And then he wanted to do a physics PhD, and so he did it. And he graduated, and now he teaches physics. So I believe he's a lecturer still at Ohio State University. So if you want a career in physics, it's actually timeless and ageless. All ages welcome. It's not like American football, right, where, I don't know, seems very violent. It's more like a tennis thing, you know, you can play at all ages. So, anyways, we'll come back here. However, there are about 400 billion suns in our galaxy. 400 billion. And at least as many galaxies in the visible universe, even if every star was compressed down to the size described above, and all the stars and all the galaxies were packed closely together, they would still encompass a volume as large as that of the Earth, implying, by the way, in case it ever proves useful to you to know it, that one can fit as many basketballs inside the Earth as there are stars in the visible universe. Goodness gracious! So did you know that as many basketballs that can fit inside the Earth are pretty much however many stars there are in the visible universe? So not that many. It's fine. We have one more large step to take. Are you ready? Uncertainty means that there are errors on your answer. So it is the opposite of being deterministic. So uncertainty, so generally when we make a measurement, there is some error. There are error bars on that measurement. You can say this stick is 10 meters plus or minus 1 meter. Let's say because you're bad at making that measurement, or you have some limitation with your instrument where your measurement can only be so accurate, and so you have to include the error bars of 10 meters plus or minus 1 meter, okay? Now in quantum mechanics, uncertainty is intrinsic. It's a part of nature, to where no matter how much you try, you can only measure things with so much certainty. There's always a little bit of error in your measurement, and it's not to do with how good or bad you are at the measurement, but just the nature of the science. Because I wonder, I remember at one point we mentioned how, say if you want to calculate the position of a proton within a nucleus, and you shine like a light on it, like a photon on it, to do that, well, at those scales, light will manifest its particle nature, and depending on also the energy of the light that you use, it's going to be a photon. If it's a high frequency photon, it's going to be an even more energetic photon, and you're actually going to push the proton or the electron or whatever particle you're trying to measure by shining the light on that particle. So you're going to add some uncertainty to your measurement of the position of that particle. So we say that if you know the position, you cannot know the momentum, and if you know the momentum, you cannot know the position, certainly, with certainty. There's always going to be errors on your measurement, and this type of error on your measurement is called uncertainty. And there is an uncertainty principle in quantum mechanics which basically not only acknowledges that such uncertainty is intrinsic and a nature of quantum mechanics, but also gives you a way to quantify your uncertainty limits, like exactly how much uncertainty there always will be, and it's called the uncertainty principle that you can look up, okay? Hello, Mr. HS, says Karma. Hello. You're more into spirituality. Our whole paradigm is about to shift. There is no age limit. Of course not. Physics is extremely ageless. You can definitely do physics at any age. Go for it. Okay? And come to these lives. These lives are ageless. Certainly. Certainly. Don't ever feel limited by anybody. Don't let people tell you what you can or cannot do. Okay? So, interesting. So, oh, by the way, can someone do a super chat? That would be most helpful. So, even if every star was compressed down to the size described above, and all the stars and all the galaxies were packed closely together, they would still encompass a volume as large as that of the Earth. We have one more large step to take. That's where we're at. Compress all of this mass, 160,000 billion times the mass of the Sun, down by another factor of 10 million in radius. The matter in the entire presently visible universe is now contained in a space the size of a baseball. So very extreme compression here. The mass of a teaspoon full of this matter alone equals as much as 1 million galaxies, containing a total mass of 1 billion times that of our Sun. In the space traditionally occupied by a single atomic nucleus, the amount of matter contained would be more than enough to construct all of New York City. In the space traditionally occupied by a single atom, including the region in which the electrons normally orbit, the amount of matter would be almost the mass of the entire Earth. These numbers may seem staggering, but they do not tell the whole story. In fact, they miss the most important part of it. As one compresses matter, the energy exerted heats the material up. Because compression is not free, remember? When you're putting work in to compress things, you're adding heat to this material. A larger and larger fraction of the total energy of a closed system is contained in the radiant energy emitted and absorbed by the hot particles. So once again, a larger and larger fraction of the total energy of a closed system. So this thing that you're compressing, it's going to have some total energy, but you're adding energy to do this compression, and a larger and larger of the total energy of this system that's been compressed with energy to compress it is going to be contained in the radiant energy emitted and absorbed by the hot particles. Hot particles radiate energy. So these things that are being compressed are not just going to be like, oh yeah, let's compress each other and be fine. No, they're also going to be radiating energy, and a lot of that energy will actually be emitted as well as radiant energy, and absorbed as well as absorbed by the hot particles. Well before the whole system is compressed to the unfathomable levels I have described above. In fact, when the observable universe is compressed by merely a factor of 10,000, about 1 million light years across, its energy would be dominated not by matter, but by the energy of radiation. So if you remember in our cosmology lives, we mentioned how in the beginning of the universe, it was a radiation-dominated universe, remember? It was considered to be a radiation-dominated universe. Now, do you kind of start to see where we're going with this? When you compress things to that very small radius, you have added energy to compress, and also those things are heated up. And actually, more than the matter now, what's happening is that it's dominated, this environment is dominated by radiation, radiant energy. And you like totally my type. Type of what? Hello, Kali. How are you doing? So, that's how the beginning of our universe was, by the way. So I don't know if he's about to talk about our universe. Hopefully he is, the beginning of the universe. And the beginning of the universe was extremely radiation dominated. Oh gosh. Okay, so the radiation at this point is so hot and dense that it beats out the gravitational pull of all 160,000 billion stars. But by the time we compress the visible universe down to the size of a baseball, the fraction of the total energy associated with the mass of all the matter making up all galaxies today is only about 10 to the minus 25, or about 1 part in 10 million billion billion. Yes, the cosmic microwave background radiation. It's from around 300,000 years old of the universe. When the universe was around 300,000 years old, which is still very early in the universe, that's where the cosmic microwave background radiation is from. Yes, Eversora is asking about that or saying something about that. So by the way, Chickpea, are you still here? Are you listening to your favorite book? Insane. I know. Isn't that so crazy? So crazy. By the way, thank you so much everybody for being here. Can you please like the live? Can you like, share, subscribe, tell your neighbors, tell your cousins about this live and about this channel, and please do come and visit us and come to these lives. We do cats and physics here. And can you please like the live, and can you please do a super chat? How about that? To support us and this channel and to let us keep going with it. So this radiation has a huge pressure. So something I should have mentioned and I thought about it was radiation pressure. When something radiates a lot of energy, there's actually radiation pressure associated with that. It's like almost like say there's this like hot thing. It's not just going to be a hot thing. It's going to be something that like exerts pressure out, right? You can't like, there's going to be in the past, at one point the universe was 300,000 years old, and we have a radiation from that time that we can still pick up on, and that one is called the cosmic microwave background radiation. Okay? Yes, the Earth is 4 billion years old, and the universe is more like 14 billion years old. So there was a time when the universe was much younger. So when the universe was much younger, back in the young days of the universe, there is a signature of photons that we pick up on from that time, okay? So this radiation has a huge pressure, and it does work on an expanding universe. So that after a few thousand years, its energy dwindles away and it becomes negligible, leaving just the matter contribution to dominate the universe today. So by the way, he was kind of implying that all of that compression is kind of like how the universe was in the beginning. I think he hasn't said it actually. So I'm guessing he's talking about when the universe was getting started, it would have been radiation dominated. He hasn't actually said that. But let's see. He's saying the fraction of the total energy associated with the mass of all the matter making up all galaxies today is only about 10 to the minus 25, or about 1 part in 10 million billion billion. This radiation has a huge pressure, and it does work on an expanding universe. It does work on an expanding universe. So that after a few thousand years, its energy dwindles away and becomes negligible, leaving just the matter contribution to dominate the universe today. Thus, while in the region normally occupied today by a single atom, the matter contained at that time would have a rest mass comparable to that of the Earth. The actual amount of energy contained in this region, including radiation energy, would have been much larger. In fact, it would correspond to the energy of the entire presently visible universe. Yeah. Wow. The universe in an atom. So he basically wanted to give us sort of certain scales and certain numbers to kind of orient us to what it means when a bunch of things, when a bunch of matter is compressed down to a very small volume that it occupies, and what types of energy and radiation and radiant energy it would entail. And pretty much that's kind of, I think he's alluding to the beginning of the universe. I don't see any other reason to really mention all this. Let me see what he called this chapter, because I started the universe in an atom. So he's not really saying Big Bang or anything, but okay, he wanted to give us certain scales of things. That's fine. That's fine. So anyways, we'll keep going. Let's see where he takes us in this chapter. But we know that shortly after the Big Bang, when the universe got started, the universe was extremely radiation dominated, and some of the stuff he's saying here is exactly matching with that. Like, it used to be much smaller scale, things were very hot, things were very together, hot, dense soup, and it used to be a lot more radiation dominated. Let's pause and reflect on our voyage. Even after the baby steps, it is still mind-boggling to try to picture what conditions are like when each atomic volume contains an amount of energy equivalent to that contained in our whole visible universe today. It's true. It's difficult to imagine that the whole visible universe today could have been contained in a volume as small as the atomic volume. Can you believe that? Like, that's crazy. But you may wonder whether it is even worth trying. After all, under such conditions, the whole meaning of atoms, the protagonists of our story, dissolves. How can we connect individual entities like the oxygen atoms that help make up the molecules of our DNA with anything in that incredible morass? You also might have wondered why, if we're going to go back this far, we don't go back all the way and begin our story at the infinitely dense Big Bang itself. Thank goodness he's mentioned something about it. Let's address the second concern first. The reason we do not take our story all the way back to t = 0, which is when the universe got started, is that this instant is still shrouded in mysteries. Hi, Baji. In mysteries beyond our scientific purview. So there is nothing concrete to say. But we do not think we have to go all the way back to t = 0 in order to understand the origin of our atoms. We believe that the Super Kamiokande experiment, so sometimes called Super K experiment in Japan, or a larger one that may follow it, may allow us to infer the events that would have had to occur at the precise moment when the existence of atoms in our universe first became a real possibility. Chickpea, are you here or not? If she's 9, she's fine. That's what I'm saying. Okay, I don't know what that means. I think Chickpea has fallen asleep. Chickpea, my friend, have you fallen asleep? That's okay. So, and to respond to the first concern, that moment occurred very early in the history of the universe. It is appropriate to argue that each atom in our bodies began life precisely then, even though atoms themselves would not exist for what would seem like an eternity at that time. Yes, Chickpea's a mod. Chickpea's a mod, and there's Baji. Although no events have yet been observed in the Super Kamiokande tank that would let us recreate with some certainty the events at that time, we know that a specific subtle series of events had to occur in that primordial baseball in order for our oxygen atom to exist today. So subtle, and rare in fact that had anyone been around then to notice what was taking place, they probably wouldn't have. Indeed, it seems that without an early series of rare events, at least as rare as a single person buying 2 winning lottery tickets for 2 different state lotteries in the same year, no one should be around today to celebrate creation or lotteries. No, I'm asking because this is his favorite book that he has been requesting, so I want to know, is he missing all this or not? The mod is fine, because I think most people are behaving at the moment. Nevertheless, there is a maxim I'm consistently or constantly reminded of in my work. Because the universe is big and old, no matter how unlikely something is, if it can happen, it will happen. Aww. Accidents more remote than anything that might occur. During our lifetime occur every second somewhere in the vast reaches of the cosmos. The most important question of modern science, and perhaps theology as well, is then, are we merely one such accident? Because Super Kamiokande has not yet given us the empirical evidence we need to infer precisely what series of events occurred at this early time. We only know that some specific challenges, which I shall describe, had to have been met in order for our oxygen atom to exist today. Wow. In this sense, the story of our atom takes on a Rashomon-like quality. In his famous film Akira, Kurosawa followed 3 different versions of the same event. Because of their different vantage points and their different past experiences, each describes a different story. None is universally accurate, but each contains at least a germ of truth. If atoms could speak, each would have a different story to tell, but we expect that the beginning of all these stories, when our universe could fit inside an atom, would be the same. Its rough outline has begun to emerge over the past century as scientists have carefully recorded and analyzed the signals nature has provided. The event we await at Super Kamiokande, or an experiment that may follow it, will, we hope, nail the details. So they're pinning a lot of hopes on the Super Kamiokande experiment in Japan or its next generation experiments to kind of give us some of these answers. Until then, the following story is guaranteed to contain at least a germ of truth. So the next chapter is called The Right Stuff. In order for the wheel to turn, for life to be lived, impurities are needed. So that's, this is where we will end our chat or our reading tonight. I want to pick it up tomorrow, and I want to make sure that Chickpea is in the chat when we do. So I think I'm going to go live earlier tomorrow and not so late. Please do like, share, and subscribe, everybody. Thank you so much. Please do like the live, share the live, comment, chat message, all of that stuff. I'm looking at my channel. Please do subscribe. And please do come again tomorrow. We will keep on keeping on, and we will continue this discussion, and we will continue more about astronomy and astrophysics as well, if you're interested, because those are some pretty hot topics and favorite topics of mine. Cosmology, of course, as well. And we will pick it up from the chapter 2 of this book by Professor Dr. Lawrence Krauss. Okay? Thank you so much, everybody. Thank you, thank you, thank you. Baji's ready for you. Here's some Baj. And here's my face. Good night and sleep tight. That's what I was talking about earlier, Eversor. What grows on Earth is the rarest thing in the universe? Trees, spirituality. So somebody made a spiritual prediction earlier about something shifting. Say more about that before I go. What is shifting, and what spiritual stuff do you have to share with us? And by the way, if you're seeing this as a live replay, as a video upload later on, which it should be under the live tab of the channel, please do leave your comments, like, share, subscribe as usual. Thank you so much for being here. Do share your thoughts in the comments. I'm always happy and looking forward to read them when I wake up. Okay? Hasta mañana, young professor. Hello, Acacio. Good night, Acacio. Enlighten us, Eversoar. Yeah, so what was Eversoar? I think it was Eversoar. Somebody was saying some shift in the paradigm for in spirituality. Tell us. Consciousness is fundamental. Consciousness is fundamental? No matter. What do you mean? I'm interested. I'm interested. Hello, Mayrana. How are you? Welcome, Iran. How are you? I'm still waiting for Eversoar to say more about the paradigm shift. Still typing? Morteza, hello. Thank you for the emojis. Matter comes from consciousness, not the other way around. Okay, well, say more. Can you say more? Thank you for liking the live, everybody. Can someone do a super chat? That would be most excellent. Please do help to support this channel so that we can continue all this cats and physics type of stuff. It's very difficult without any support. Okay? Please do help us. I'm actually replying to my member, Steven, who became a member recently. So
today my friend asked me to hang out.
Sorry, my face is too close to the screen. I'm looking at the video where he commented and trying to reply to him about something. Oh gosh. Hi, Sachi Mama. Suji Mama is over here getting my attention. I thought paradigm shift was the North Pole moving to the south. What do you mean? What? By the way, guys, if you're joining right now, can you please rewind so you can see the full live? Please do rewind, okay? Oh my gosh, Acacio. Thank you. Oh my gosh. My friend. Rachid Mudgal says hello. Hi Rachid. Hello Eversor. Eversor means consciousness is not a product of the brain. It exits outside our body. It's non-local. Where do you live? Morteza says, where do you live? I live in North America. That actually makes sense, says Jeep. Acacio, my friend! Thank you, amigo. Gracias. Muchas gracias. Thank you so much. Thank you, 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 thank you. Acacio has done a super chat. Thank you so much. Please, everybody, thank Acacio. Thank you for your support. It really helps to keep the channel going. The cats and physics stuff, the physics classes especially, it's going to be very difficult to keep them going without your much needed support. So thank you so much. Really appreciate you. Let me respond to Stephen, who is a member. Another way you can support is to become a member. What is he saying? I'm your only member. Yeah, I know, Stephen. We're gonna read Stephen's book on like Monday, on like Sunday or Monday. Acacio says you're welcome, my pleasure. Thank you, Acacio, my friend. Thank you so much. You are so kind. And Acacio has supported in the past as well, so I'm much grateful for the support, Acacio. Thank you so much. So I'm telling Stephen where is his friend, because Stephen's book reading will be, here's Baji. His current trick is to show you that he can sleep. So Stephen's book reading, like I think I'm gonna do like a full chapter from his book for members only. And so I'm asking him, where is his friend? Is he gonna become a member or not? And I'm gonna keep the live streams mostly like physics topics, like what I've been doing. Like I really want these physics classes to keep going. I don't want to stop doing the physics classes, because honestly I really love to teach these topics and to talk about these topics and to discuss them with you live. So that's why the super chats and memberships and everything, all the likes, shares, subscribes, the growth of the channel really helps with all of that, and the super chats especially really help. But since we're also kind of like a book channel, like a booktuber, book talk, book club vibe, thank you for the heart emojis. Thank you guys. So we are also kind of launching some people's books, and Stevens is one of them, and it's a science fiction. So I don't want to confuse like the science with the science fiction. So like the science fiction will be like, maybe I'll read a page out of his book as part of like the live one of these days, and I've kind of done that in the past as well. But then I might make something members only for his, like for a full chapter or something. So I'm talking to him about that in the members only section of the channel. So if you want to join as a member, feel free. Most welcome to. Nice to meet you, says Marteza from Netherlands. Welcome to Netherlands. Welcome to the live. I don't see him as a member yet. I'll tell him. I don't see him as a member yet. What do you mean? What do you mean, Steven? UFO fiction or reality? So I think his book, it's like a Star Wars flavor of science fiction. That's what his book is. So if you're new to the live stream, by the way, most welcome. Please do come to many of these live streams. We go live almost every day. So please join again, and then that will give you a flavor for like how we kind of rock and roll, okay? I know it can be like kind of a lot to like join one day and be like, okay, what the heck is going on? But please do keep coming back, and you'll see much better about like sort of the context of these episodes and the stuff we share, and you'll see a lot of people are friends with each other, and they become friends in the chat, and they like hang out and kind of catch up with each other as well. It's kind of like a class with a lot of noisy, talkative kids. Okay. Spirituality is science, asks Jeep. Thank you, Acacio, once again. And everybody, did you subscribe and did you like and share? Okay. Okay. I will see you guys I will see you guys tomorrow, okay? That's so funny. Gosh. Steve is saying hi to me on all the videos that are I think he's having fun as a member. He's been leaving me comments on all the different content. Okay guys, thank you so much everybody. Good night, sleep tight, okay? Bye.